Hello, this is Kate Lee from University of Auckland. In this talk, I will present Bayesian calibration with EMRI application. EMRI stands for Extreme Mass-Ratio Inspiral. It is in spiral of a secondary small mass into a primary supermassive black hole. Because of the extreme mass ratio between secondary and a primary mass, it can be eccentric and inclined even up to last few cycles before plunging into the primary mass black hole. The scientific interest of EMRI is that it is one of a promising source for gravitational wave in laser band. There has been several models being proposed to explain the behavior of EMRI waveform. Given observed waveform, the parameter estimation will be an interest because if you know what parameter should it be, then you will be able to explain the physical behavior of EMRI waveform. In this talk, we'll look at the Bayesian inference for a parameter associated with waveform model. I will introduce three notation. H star is observed waveform, theta is parameter associated with the waveform model, and H theta is a waveform generated from a model using theta value. Instead of point-wise estimate based on loss function, we will estimate the probabilistic uncertainty around theta given observed waveform. That is so-called posterior distribution, which is denoted by this. And the posterior distribution is known to be proportional to likelihood times prior. So prior is a prior information about theta before we see a waveform. And likelihood simply measures the goodness of fit between observed waveform and waveform generated using theta. In this talk, we'll focus on two models. First model is called a semi-relativistic numerical closure, so-called NK, which is known to be highly accurate but very expensive. In other words, waveform generated from NK can be treated as an exact waveform. The second model is augmented analytical closure. It is known to be faster to compute than NK, but it is less accurate. So in other words, waveform from augmented analytical closure model will be treated as inaccurate model. Hence, posterior with the likelihood using NK will treat it as exact posterior, and posterior distribution with likelihood using AK will be treated as an approximate posterior. When you use a likely approximation, then the resulting posterior is no longer exact. Hence, your inference is likely to be damaged by the usage of likely approximation. The question is whether we can estimate such damage. If we can quantify the damage in inference due to the usage of likelihood approximation, then we will be able to make more sensible decision. If damage is acceptable by your standard, then you may keep using an approximation. If damage is not acceptable, then you may need to look at more accurate model for your inference. In this talk, we will use operational coverage property to measure the damage. The operational coverage is simply the coverage of exact posterior over credible set approximation. So here's a credible set approximation is a credible set of approximate posterior. So here's a two diagram to illustrate the idea. The black curve indicates exact density, exact posterior, and solid red curve indicates approximate posterior density. two red vertical dotted vertical bar indicates 0.9 credible set approximation. So in other words, they are 0.9 credible set of approximate posterior distribution. Left-hand side plot, there is no approximation. Exact approximate posterior as sign. Operational coverage is represented by grayed area. So as you can see, that is simply the coverage of exact posterior for over approximate credible set. Because there is no approximation, the coverage will be nominal value, which is 0.9. Right-hand side, there is some deviation between approximate and exact posterior densities. Approximate density are shifted to the right-hand side. Hence, credible 0.9 credible interval approximation is shifted towards the right-hand side. Operational coverage is a coverage of exact posterior over approximate credible interval. And as you can see, the operational coverage will not be the nominal value. It will be small or bigger than nominal value. So if operational coverage is close to nominal value, that indicates approximate posterior is very close to the exact posterior. If approximate posterior is very different to exact posterior, the operational coverage will be very different to nominal value. So here's a mathematical formation of operational coverage. Pi tilde indicates approximate posterior, pi indicates exact posterior, c tilde c are the resulting credible set. Simply operational coverage probability is the probability that phi, which is a random variable of exact posterior distribution, belong to credible set approximation given observation. Now, things about this approach is that we can measure the damage at the observed waveform. So here's a simulation study. We'll do a Bayesian inference for primary and secondary mass. Our observed waveform is a 1 day long NK signal with a primary of million and secondary mass of 10. And we assume there is no noise in our waveform. And here's our posterior. So exact posterior will be conducted by using likelihood with NK signal. Approximate posterior is conducted using likelihood with AIK signal. We did an inference for various distant measures, t from 0,1 to 0,3. So first diagram, this diagram shows exact credible set, 0.9 credible set, which are colored by blue, and approximate credible set, which are colored by pink. X-axis shows a primary mass value, y-axis shows a secondary mass value, and this two-bar intersection indicates the true value. And as you can see, there's some overlap between approximate and exact credible set, but there's some area which are not disoverlapped. But as you can see, the exact credible set has a centered at a true value, whereas approximate credible set are a bit shifted away. And the middle one is when d is 0.2. There are more overlap between exact and approximate credible set. But on the other hand, both exact and approximate credible sets becomes a bit larger. So in other words, there are more uncertainty around secondary and primary mass estimation. When d is 0.1, there's really good overlap between the approximation and the exact credible set, but again, its uncertainty also gets bigger. So here's a table showing operational coverage estimation, which are indicated shown in the third column. As d increases, from this diagram, we've seen there more overlap between exact and approximate curve set, hence operation coverage probability increases towards 2.9, which is nominal value. But on the other hand, as the increases, the uncertainty on primary and secondary mass estimation also increases. The last column is a operational coverage estimation without using exact posterior calculation, which we will not talk about in this talk. In summary, we demonstrate how to diagnose an approximation using coverage of a curve set approximation. Operational coverage estimation can be done with or without exact posterior simulation. But if you don't use exact posterior simulation, then you need some extra computation to deal with it. Once you estimate the damage, okay, and damage is not too big but not quite acceptable, then you may consider recalibration. So here's a couple of recalibration idea. First one uses Gaussian process prior, and second one uses distortion map for recalibration. Thank you for listening to my talk, and this is joint work with Renate and Matt and Ollie and Patricio and Alvin.